Hi, everyone. I want to welcome you today to the Nature Conservancy's Lunch and Learn. We're so happy to have all of you here with us today, and we're so excited to have both Will and Vinayak here to share some of their research. During the presentation, if you have any questions, I'll be monitoring the chat, so you're welcome to put it in the chat, and if it's really time sensitive, the speakers have said that it's okay to come off of mute and want to ask your question directly in the place where it belongs. So I'm gonna turn it over to our speakers today, allow them to introduce themselves and start sharing their screen and get our program underway.
Okay, I'll go first. I'm Will Osterholz. I am a research soil scientist with the USDA ARS, the Soil Drainage Research Unit in Columbus. I'm guessing a lot of you know Kevin King, and I work with him in his unit. Just to give you a little context. Vinayak?
Good afternoon, everyone. I'm Vinayak Shedekar. I'm a research scientist in the Food, Ag, and Biological Engineering Department at Ohio State. And I've been working in the department kind of hand in hand with the USDA ARS unit, as well as some of the OSU side of folks. And bit of a background, I guess. I've been working on this nexus between soil health and water quality. So that's what we're going to talk about today. The other program that I'm involved with is the Osterholz Drainage Education and Research Program. Many of you know Dr. Larry Brown, who was the director of the program, and I have the interim responsibility for the drainage related extension work in the state right now. So that's a little bit about me.
Okay. Well, we have some good information to share and a fair number of slides to try to get through. So I'm gonna go ahead and get right into it. So hopefully I can share this. And presentation mode. Okay, I think you all can see this now. So yeah, today Vinayak and I are going to be focusing on this question: can cover crops and no-till improve soil health and water quality in Ohio? And this question is really the core of a research project that we're collaborating on. That was funded by the SARE program, by a SARE grant. So the motivation behind this project, there's good evidence out there that cover crops and no-till can improve soil health, especially when they're combined together. So they form really the core of what we could consider a soil health management system. And just, to share a little bit here, some data that Vinayak actually collected in a past project where they looked at a number of different fields varying in the length of time of soil health management. So again, thinking about cover crops and no-till, they went from basically a field that had never been under soil health management on the left side, all the way over to a very mature long-term soil health management system, and measured, in this case, soil organic matter. And they saw this nice increase due to that soil health management. So, this is not especially noteworthy based on, what we know from the literature, but it's good evidence that this is the case, and this can be observed in Ohio. And they also measured microbial biomass, which is obviously a very important indicator of soil health. And again, they saw some increase in microbial biomass from the no soil health management up to that very mature system. And sort of an interesting point they saw here, which we're not really going to get into today, but they actually saw a big difference in the fungi to bacteria ratio. So they saw some evidence that the microbial community was actually changing based on that soil health management. But maybe we could talk about that later if you have questions, but that's not really the focus today. So we know that this soil health management leads to improved soil health. Okay, we've seen this multiple places, but maybe the more uncertain question is, does good soil health also equal good water quality? So there's actually surprisingly little evidence to support this connection between good soil health and good water quality. So that's really the focus of our whole project here, is to try to understand if there's a connection here, and also, does it matter if the soil health systems are mature versus transitional? So what we mean by that is a mature system is something that's been in place for decades. The soil has really had a good amount of time to respond to that management system. And then something that's transitional would be, in place only a few years. The soil is maybe still evolving in response to that management. So in Ohio, obviously the water quality conversation is dominated by nutrient losses. So phosphorus is the huge concern in the Lake Erie watershed. We know that runoff drives those algae blooms. And then nitrogen, clearly a huge concern as well, especially in the area of Ohio that drains down to the Gulf of Mexico. A little later in the presentation, Vinayak's going to get into some results of both phosphorus and nitrogen losses. So to try to answer this question, connecting soil health management systems with soil health measurements and then with water quality measurements, we have this, as I mentioned, a SARE-funded research project, Soil Health and Water Quality Nexus in Sustainable Agri-Ecosystems. And this is a big collaborative effort with a number of Ohio State folks and then some of us over on the USDA side. And today we're going to focus on two research locations we've developed as part of this project. One is up in the northwest corner of the state, and then the other one is just southeast of Columbus. So both of these locations, we have paired fields. So we have one field that we call the soil health fields, and that is a field that's been under soil health management, so primarily things like cover crops and no-till, for at least 20 years, Vinayak, is that right for both of these soil health fields?
The DB would be under close to 50 years under no-till and cover crops, and the DM would be close to somewhere between 25 and 30 years under no-till and cover crops.
Okay, so we paired each of those long-term soil health fields with a conventional field nearby. We wanted these fields to be as similar as possible. It's always a bit of a balancing act. Nothing's ever going to be perfect, but we did our best to find a good pair that we could hopefully compare and get a sense of what effects that management was having on the soil health and water quality. So just a few different properties here of these different fields. One thing I want to point out is that in this Northwest Ohio site, we actually had a bit of a difference here in the texture of the fields, where our long-term soil health field had some more sandy loam type of soil, so a little bit more coarse textured compared to our conventional field, this SJ field here, which was more dominated by a loam soil type. So that'll be important in a minute here when I start talking about some of these results. But we did conduct soil health assessment on each of these fields. We did a whole suite of different indicators. And today I'm just going to in the interest of time, I'm just going to focus on a couple of these. So I'm going to talk about just the organic matter, which I think everyone is probably familiar with what organic matter is. And then also a wet aggregate stability measurement. So this is a measurement of basically you take the soil in undisturbed state, straight from the field, and you subject it to some agitation while it's wet, and you measure how quickly and to what degree the aggregates of soil break down. And this is a good indicator of structural stability of the soil, and it can be associated with things like infiltration rate. So it's an important sort of physical soil health measurement. Okay, so let's jump into some results here. So this first slide is showing the results from our South Central Ohio field. And I have the field names down here next to our treatments. So I actually have those switched, don't I? So DB actually was the long-term soil health field. So that's the brown color. So that's the one that's been under soil health management for 50 years. And then the MH field should be the yellow color here. And then I didn't mention this, but we also took some samples from a woodlot nearby just to get an idea of what a more natural system might look like from a soil health perspective. And maybe unsurprising to a lot of us, but that woodlot definitely had the highest organic matter levels. So that just gives us an idea that in a natural system, we can really get good soil health. And maybe we still have room for improvement even in our long-term soil health field if we want to try to move more towards a natural system. But then if we look at comparing the conventional and soil health fields, we can see that we did see a slight improvement in organic matter content in that long-term soil health field compared to the conventional fields across all of these different soil depths. So these first set of graphs or first set of bars here is showing the topmost depth. And then you can see as you go deeper down the soil profile, how those trends look. And this pattern was pretty consistent across all of our indicators, where we saw a slight increase of soil health in that long-term soil health field. Now, at our Northwest Ohio site, we have a bit of a different story. So again, I have our soil health field and our conventional field switched. Sorry about that. But that brown color should be the DM field. That would be the long-term soil health fields. And then the yellow color is the SJ field. And at this location, again, we see that the woodlot definitely had the highest organic matter contents. So again, probably room for improvement even in our soil health fields if we want to try to move towards a natural system. But maybe more interesting here is that the conventional field actually had slightly higher organic matter levels than the long-term soil health management field. And what we think is happening here is this is probably a texture issue. So as I mentioned earlier, our long-term soil health field actually had some more sandy type soils than compared to that conventional field. And it's pretty well established that soil texture has a very strong influence on how much organic matter we see in soil. So we think that that's maybe just a pre-existing difference between these two fields. And so we're hoping that, maybe taking some additional measurements, we could see how maybe these organic matter levels might vary within the fields, and if we can better understand what exactly is happening in that conventional and soil health field. And then the last soil data I'm going to show here is these water stable aggregate data. So here again, we have, this is just from our South Central Ohio site. We don't yet have the data complete for the Northwest Ohio site. But if we just look at these Southwest Ohio fields, the MH here is the conventional fields. And then DB on the bottom is our long-term soil health field. And for this one, we actually took some samples from what we call a transitional soil health field. So this is another field nearby, right next to the DB field that's only been under soil health management for about 5 years. So we would consider that a transitional field, obviously not as mature as that 50-year DB field, but starting to get that management system underway. And what we can see with the aggregates is that both the long-term soil health field and the transitional fields, even after just 5 years, we saw a significant increase in aggregate stability. And particularly with the largest soil aggregates. So the different patterns on these sections of the bars here indicate different sizes of aggregates. And what we saw is that the medium and largest aggregate classes, actually, that's where the increase was from that soil health management, which is what we like to see from a soil health standpoint. It's those large aggregates that take a long time to develop and indicate a very stable soil health system, indicate good soil structure, and can be connected with good water infiltration into the soil. So that was just a quick overview of some soil health measurements we've taken and the patterns we're seeing at these different locations. And the rest of our time we're gonna use to discuss the water quality measurements and results. And this slide just gives a general overview of our water quality monitoring setup. It's pretty standard. We've got a pretty good system developed in Ohio for how to do this. So we have a rain gauge out there. We've got solar panels to provide us power. We've got a V-notch weir, which goes in the tile drain to measure the tile drainage. We've got a flow meter, an automated water sampler to grab samples at different intervals. And then we have an H-flume that is in place to capture any surface runoff. So we have both surface and tile drainage monitored at these locations. Okay. So yeah, tile drainage. Again, just giving you an example here, what that looks like. And then surface runoff at both fields as well. Just giving you some pictures there. So I think we're gonna take a pause here. And if there's any questions up to this point, we could address those. Otherwise, I'm gonna hand it over to Vinayak to talk about the water quality data. So any quick questions at this point? All right, well, Vinayak, why don't you take the reins here?
Thank you, Will. Gonna try to share my screen. So while we're on this slide, I wanted to just maybe, I know we didn't get questions per se, but if any of you want to unmute and just kind of make a guess, we're talking about the mature soil health field versus a conventional. In the audience, is there anyone who wanna chime in or guess what you might expect to see in terms of the water quality coming out of the tile drainage versus surface runoff? Just take a moment if anyone has any thoughts on what you might expect to see. I know a couple people in here. I can just put you on the spot. Rachel, what do you think?
Sorry, Vinayak, what was that?
I'm just trying to get someone to chime in on what you might expect if you're monitoring a field that's under no-till cover crops for 50 years versus a conventional field in terms of water quality.
Probably see better water quality off of the no-till field, I would guess.
Okay. And would you expect that consistently in the tile drainage as well as runoff?
I would think so.
Okay. All right. So as Will mentioned, we're looking at the the water quality that we're monitoring is mainly nitrogen and phosphorus losses from these fields. And I want to emphasize the fact that this is preliminary results based on 1 year of monitoring so far. But this is what we're seeing. And I always like to start with my conclusions first. So very quickly, I'm going to show you just based on one field, which is very consistent with the other field. We're seeing about 2 inches per year less water discharge, which essentially means surface plus subsurface discharge. So tile drainage and runoff together. About 2 inches of water, less water leaving a field under a long-term soil health system. About 50% less nitrogen leaving the field that's under long-term no-till and cover crops. And about 25% less dissolved phosphorus loss leaving that long-term soil health field compared to a conventional field. And I'll talk in more detail about all of these results. I just wanted to start with the conclusion, kind of orient your thought process there. So that was the data, the summary based on the entire calendar year of data. Here is a more of a zoomed in version where we're monitoring the data at a 10-minute interval. And this is tile drainage discharge that we monitored. And the red field, the red line that you see, so the blue line is the rainfall. And here's the axis for that rainfall. So it was a pretty sizable rainfall event. Can't see my own slides here because of the Zoom tools, but it's about 0.6 of an inch rainfall. And in spring, so conditions were pretty wet. And then we see a very quick response to that rainfall in terms of tile drainage. The red color is the discharge that you observed at the conventional field. And you can see there is more water leaving that long-term soil health field. So you might think, oh, well, yeah, there is more loss happening here. Well, if you remember that long-term soil health field was actually larger field than the conventional field. So if you normalize the total loss of water through tile drainage for the area, then there was about 50% of that rainfall that translated into tile discharge in the conventional field, where only 30% of that tile discharge translated of that rainfall translated into a tile discharge from the long-term soil health field. So even if the volume leaving was more, the depth-wise per acre basis, we had less water leaving the mature soil health field. Similar observation with respect to surface runoff. This was not rainfall driven. This was a snowmelt driven runoff, and we see a kind of a spiky and high discharge coming through the surface runoff, and kind of a lesser of a response from the long-term soil health field. And note that, in the month of February, there is cover crops growing and residue that already exists on the ground. So there's pretty good opportunity for that water to have that resistance, which helps minimize the flow of water through the runoff. So here is the big picture in terms of how much of the total water left these fields. And we're gonna look at things, the quantities in inches. And just to orient you with what we're talking about, again, that DB was the long-term soil health field, and paired with the MH, which was the conventional field in the south central Ohio. And then this pair here was from the Northwest Ohio. Again, the DM site was the long-term soil health field, and the SJ was the conventional. And you can see this greenish bluish is the tile drainage, which is the major part of the discharge. There is a small amount of water that leaves your fields in terms of surface runoff. which is that orange shading here. The first thing you may notice is there is a really small amount of runoff happening from the long-term field. Our Northwest Ohio long-term soil health field didn't produce a single runoff event in that calendar year. But then in overall, as I mentioned, about 2 inches less water. In this pair, there was even bigger difference in terms of the total discharge leaving the fields. Moving on to the nitrate load, the first thing we looked at is the concentration of nitrate leaving these fields. So here is a box plot, so that dark black line that you see is the median value for nitrate concentration observed over the entire year. And then again, this blue or green shading is the tile drainage concentration in the tile drainage. Orange is the surface runoff concentrations. And then DB is that long-term soil health field. MH is the paired field. In terms of nitrate, you do see some difference in the tile drainage losses in terms of the concentration, definitely higher concentration, but still well below the 10 ppm standard for the drinking water quality. Again, a lot of variability in surface discharge, but very low concentration of nitrate leaving. In terms of the Northwest Ohio, you can compare the tile discharge, not a lot of differences here. Again, we didn't have any surface samples to compare with the conventional field here. Concentration data can only tell you so much, but if you multiply the concentrations with discharge, then you get the actual amount of nitrogen that left that field with that water. And now you can start seeing some of the differences between these treatments. So DB and DM are the long-term soil health fields. And again, these conventional fields tend to have very high, I shouldn't say very high, but relatively higher nitrate losses compared to the fields that are under long-term no-till and cover crops. And this is this is proven in the literature. There is many studies that can easily, that have concluded the same thing. And the biggest difference between these two fields is the fact that this DB and DM have active roots and living plants during the non-growing season that are taking up that nitrogen, and that tends to play a bigger role than the discharge itself. So a lot of uptake of nitrogen happens in non-growing season, and that's what causes this huge difference, up to 40-50% lower, less nitrogen leaving these fields. Will helped us put this together, put this in a context of all the data that Kevin King and his group has been collecting. So this is on the left that you see is the nitrate loads observed from all the edge of field sites that USDA ARS has been monitoring. And here is our sites. So on the same scale. So you can see that our sites in general are already producing very less amount of nitrate load, but within that small group, we do have our long-term soil health sites that are producing even lesser nitrate loads. Let's talk about the nutrient loading that is of our interest from the Northwest Ohio perspective, which is the phosphorus losses. And this is the dissolved phosphorus concentrations in the tile discharge, which is that green, and then the surface runoff. And something that highlights here right away is someone might think, oh, they look at this long-term soil health field. There's such a high phosphorus concentration compared to that other conventional field. So maybe there is a problem here. Maybe we have more phosphorus loss because you have higher concentrations. But again, if you remember that lower discharge comes into the equation here, in general, we did have greater proportion of dissolved phosphorus loss from our long-term soil health field. But if you take the total loss of phosphorus, dissolved phosphorus, it was much less compared to the conventional field. This was for that South Central Ohio. Northwest Ohio was even bigger difference. Again, we did not have any runoff to monitor. But just taking the totals for the dissolved phosphorus losses between the long-term soil health field and the conventional, we did observe that much less dissolved phosphorus leaving that soil health field. If you remember Will's comment that this field actually tends to be more sandy loam texture compared to the silt loam texture. And so that's, again, there are some texture differences that we can relate with this, but it's just a very unique observation that seems to be more encouraging. In the literature, you might find some disagreements on this topic of dissolved phosphorus loss from fields that are under cover crops. There are some studies that indicate that maybe the cover crop residue and the presence of the residue and the stratification from no-till might result into greater concentration and hence more losses of dissolved phosphorus from these systems. But we're not observing that from our studies. Again, putting that in context with the edge of field data collected across up to 40 fields in Ohio. Again, very, very small amount of dissolved phosphorus leaving these fields compared to some of the fields that are part of that edge of field monitoring network. So just trying to put it in context of the bigger group there. Moving on to the total phosphorus loading. Again, if you look at the total phosphorus concentrations, surface runoff, you can see higher. Typically, you will see greater total phosphorus concentrations in surface runoff because of the presence of sediment in the runoff samples, especially if you look at this conventional field here. It had very high concentration of phosphorus because of the greater sediment losses. But again, concentration data can tell you only so much. If you multiply by discharge, the total loading of total phosphorus from the soil health fields was much less compared to the conventional fields that we're observing. So there's a lot of graphs here. Maybe a picture tells that story. Just a single picture might tell the same story that I'm trying to present here. On the left, you see just a close-up shot of the surface flume that we use for monitoring the runoff. And that field in the background is that field that's been under 50 years of no-till and cover crops. This photo was taken on the same day after a rain. I think it was a rainfall event. But you can see the flume is very clean. There's no evidence of erosion happening there. And look at the other field. This is the approach section where the water kind of concentrates and kind of goes into that flume in the conventional field. And we essentially, every time we go out there after these events, we see this evidence, a couple inches of soil just accumulated in that flume. So there is a lot of good qualities. I shouldn't say, well, it's a lot of good topsoil that this field is losing. And we do, it's really helpful to have these pictures, because even when we're working with the producers, we can show them this and, try to convince them on some of the measures that they can take to control the soil losses. Again, just wanted to come back to this slide that kind of tells you the story in general based on our preliminary results. But really the conclusion that I want to highlight here is, again, this is preliminary data. This study is meant to be a long-term study. We're hoping that we can study this over 2 or 3 crop rotations and then try to have more conclusive evidence. But in general, we did see less volume of water leaving through tile drainage and runoff, lower losses of dissolved phosphorus as well as total phosphorus as well as nitrogen. And then, of course, the nitrate is the only constituent where we could conclusively say that there were lower concentrations in the long-term soil health field. Again, want to highlight the need for the long-term monitoring of these sites But with that, I think the last slide we always dedicate to all the hard work that our technicians and our field crew puts in. We tend to monitor these systems 24/7, all days of the year. Especially winter period is really hard, and really just want to appreciate all the hard work that our team puts in here. I'm gonna leave this on and see if we have some questions. Our contact information is there.
Will and Vinayak,
Yes, Ben.
I have a question.
Mhm.
Actually, I'm Carrie sitting in for Ben. I'm on the little picture. Ben had an investor meeting come up quickly, and that takes higher priority. But he wanted me to sit in. So I'm going to ask a question, and it may be invalid by its very nature. But so my question relates to, I'll just do phosphorus because I think that's simpler. Inorganic and synthetic phosphorus, right? Organic and synthetic. That's the kind of the contrast I want to make. And so we'll pretend that the woodlots were checked for phosphorus runoff. Do we know if a natural system, a purely natural system like the woodlots, do they generate, in this case, it'd be organic phosphorus runoff? Does the question make sense?
Well, you wanna take a shot at that?
Sure. Yeah, that's an interesting question, Gary. Appreciate the outside the box thinking a little bit on that one. We know that historically, at least, phosphorus losses were lower coming out of most of our agricultural landscapes when there was more natural cover in those landscapes. I'm not familiar with a lot of work that specifically has tried to measure phosphorus coming out of more natural ecosystems, but the assumption is that it's much lower than out of an agricultural system, which would make sense because there aren't additions of fertilizer to those natural systems, at least not at the level that we do in our agricultural systems. And we also have good evidence that, at least in agricultural systems, including grasslands, there's a lot of work on grasslands, which maybe is a little more relevant. Grasslands that are used for pasture. We know that the phosphorus levels in the soil of cropland or grasslands are highly correlated with phosphorus leaving those systems. And so if we make the assumption that in a woodlot, we'd probably have lower soil phosphorus just because there hasn't historically been fertilization, we could, I think, make a pretty good guess that phosphorus losses would also be low from a woodlot.
There are some, there is microbial activity that can produce organically available phosphorus. So with a healthy microbial biome, you get phosphorus. And so, there is then, even though we're not introducing synthetic phosphorus, there is the possibility that even our best natural biomes generate a surplus of phosphorus that does get output. And I was trying to ask that then because when you have like David Brandt's fields that are 50 years of no-till, you might be approaching a natural level. It'd be nice to know where that floor was and what inputs he put in, and to really know where at a certain point it isn't a zero floor is my question. So just 28%, I'm I have to go back to my notes on the phosphorus. So there was 25% less phosphorus coming off the no-till, the soil health fields. I'm just wondering if even a purely natural ecology generates organic phosphorus, which then goes into the environment. So that while we chase phosphorus, there may be a floor that we're not going to get under. So that was questions. Actually, my question was nitrogen, which gets more complex, organic and synthetic nitrogen. So I stuck with phosphorus, which I thought would be easier. But it is just an interesting question that we're thinking about with some work in South Africa, and obviously Ohio is a better place to study it because of our rainfall patterns and soil textures. So thank you. I just wanted to think it through a little bit with you.
Yeah, I think, yeah, and then the dissolved phosphorus that we analyze here in the water samples, it's like a black box model. So it actually includes that the organic fraction in there. We don't try to distinguish between what percent of the dissolved phosphorus comes from organic sources versus inorganic sources. So we don't do that analysis, if that's what you were trying to refer to. But you brought up a really good point, that how does that relate to the management? And we meant to share the management details. And that's why we're trying to suggest that this needs to be a long-term study, is because the management between the two pairs fields technically should be the exact same crop rotation, exact same amount of phosphorus input or nitrogen input, but these are farmers' fields. We cannot control their practices. So there are differences in the amount of nitrogen and phosphorus these farmers are applying between the two fields. And in the big scheme of things, that is what makes a difference, that maybe eventually when a system matures in terms of soil health practices, it becomes a system that requires less external input of nitrogen or phosphorus, because it's more self-sufficient in terms of cycling those nutrients and retaining those. Will someone like Dave Brandt reach a point where they are applying zero amount of fertilizer? I am not sure. Based on the information we're collecting from our farmers, they are still providing a small amount of nutrients to their crops, especially in the early stages, because it is important for them to provide those, especially given the high removal rates during the growing season. So it's kind of a tricky case where we know that going in, when we're studying these systems, that the inputs are different, but that's why we're hoping that we can look at the long-term averages and say, okay, well, if you have a crop rotation based on this system, this is how the losses might look like, because you have this type of inputs coming in, if that makes sense.
But two things. One, kudos to you both for including the woodlots, right? That was very brilliant and very useful, I think, in the long-term science. So kudos there. Second thing, I won't even begin to know how to work out the science to separate organic phosphorus from synthetic phosphorus. So I won't know how to do it, but the question's valid, and the science you're doing by having a natural system like the woodlots along as a control is very useful. And so I thank you for excellent work, both of you.
Thank you.
Okay, well, thank you so much. I don't know, if there aren't any other questions from our group, I think we'll close the meeting for now. Thanks for sharing all of your research and generating not just the results, but the questions that were shared here today. So thanks everyone for attending, and thanks to our speakers. Have a great day, everyone.
Thank you.
Thanks, everyone. Bye.
Have a nice day.